All right, so today is our one and only one lecture in Chapter 6, which is an introduction to convection. It's followed by Chapters 7, 8, 9, which there are more in the areas of convection, like forced convection and natural convection. And then we cover boiling and condensation a little bit, which is in the umbrella of convection as well. Well, let's take a look at what's this chapter. It talks about the convection boundary layers. Have you heard of boundary layers before? Yeah, fluid mechanics. This whole chapter is a lot of review of fluid mechanics. All right, so we're going to have the velocity boundary layer, review, thermal boundary layer, new. But it'll look a lot like, and it'll be packaged a lot like the velocity boundary layer. Well, we'll try to develop some analogies, that's down here, between something that you're familiar with. What is C sub F? Friction coefficient, skin friction coefficient. What is Reynolds number? That's a dimensionless parameter measuring the ratio of inertial to viscous forces, often used to determine if the fluid flow is laminar or turbulent. At high values of Reynolds number, you'd expect it to be turbulent. Okay, so that is from fluid mechanics. This is from fluid mechanics. What's the Prandtl number? Well, that's a property. It's nu over alpha. Nu was a fluid mechanics property. What was that property? Yeah, viscosity, kinematic viscosity. And alpha, we've already seen, thermal diffusivity. So the Prandtl number is simply just another property. But it shows up right here. And then Nusselt number, brand new property, and it's where we get our convection coefficient. Nusselt number is h times some length scale. So the Nusselt number could be on diameter. Then the length scale would be d, just like the Reynolds number. It's like, what is my length scale for Reynolds number? Here they didn't put a subscript on it. They didn't put x, or they didn't put d, or they didn't put l. But you need to know what is the length scale in the Reynolds number, just like this for the Nusselt number. Here I'll put d for a length scale, h d over k. And that's the purpose of this chapter, is a mechanism to get the Nusselt number so that you can unravel it to get the convection coefficient, being the Nusselt number times k divided by whatever length scale. Here I put d. Somebody says, what happens if the length scale is x? Great, just put x there, and x there. So maybe that's too confusing. Maybe I should clean that up. Put Nusselt number as a function of x times the thermal conductivity divided by x, if your Nusselt number was defined that way. And then actually this would be the local convection coefficient. When in fluid mechanics you had the local friction coefficient, and then you had the average over the plate friction coefficient. We'll do the same thing. It's just a great review of fluid mechanics with something added, heat transfer. Right here, I jumped ahead of myself. Local versus the average convection coefficients. Laminar versus turbulent, something you're already familiar with. What are you going to use to determine the criteria? Well, you'll look for a critical Reynolds number, then you'll compute the Reynolds number, and you'll compare it to the critical Reynolds number. The two critical Reynolds numbers are 2300 and 500,000. What? 2300, I could recognize that as a critical Reynolds number, but 500,000, 500,000, is that really? Well, yeah, that's for flow over a flat plate. So these are the two values for the critical Reynolds number that you should remember. Okay, we take a look at the boundary layer equations to help us develop that analogy. So all of our equations are focused on getting an analogy in this chapter. So we'll have the similarity between our boundary layer equations, look at our dimensionless parameters. That's where we clearly see the Reynolds number, the Prandtl number. We see the Nusselt number, the skin friction coefficient. Somebody asks you, hey, what are the SI dimensions of the Reynolds number? What would you say? Dimensionless. Somebody says, give me the SI units for the Prandtl number. Dimensionless. How about the SI units for the skin friction coefficient, C sub F? Dimensionless. And the Nusselt number is dimensionless. That's right. So anyway, we work with dimensionless properties, which can be pretty abstract, but then they're powerful because they come in with an analogy between the heat transfer and the shear stress. Okay. And it's going to be a modified. Now this has a lot of limitations, but at least it's something that we can use as a beginning point in a lot of studies of convection heat transfer, and it forms the basis for why the experimentalist took some data and transformed it this way to generate a very generic correlation. All right, so here it is. This is the modified Reynolds analogy. That's it. That's the chapter. More than half of it is review fluid mechanics and differential equations, calculus, because when you take and introduce the Reynolds number and the Nusselt number and a Prandtl and a skin friction coefficient, basically it's a good review of differentiation and changing variables. All right, so this is just the beginning. We're going to study flow over a knife-edged flat plate. Is it a blunt flat plate like this? No, because if you had a big blunt area in the beginning, then the flow that was here would have to be pushed up and you'd immediately get a nice separation region right in there. We don't want that. Is it a non-aligned knife-edged? No, it needs to be aligned. So the flow is coming here and the axis is perfectly aligned with the direction of the flow. And is it curved? No. You can add that complexity later, different textbook, a different time, not today. So what does this do? It cuts it such that in this tip region, which is always difficult, it's always challenging, there's singularities there in fluid mechanics and in heat transfer, we get a nice mathematical expression by which we can solve for the fluid velocity anywhere over the top half of that knife-edged flat plate. All right, so we want to review our fluid velocity vector field. So at any point in the field, we can talk about V, which has Ui plus Vj plus Wk. Familiar notation, so the x component of the velocity, U, the y component of the velocity, and the z component. Well, today, forget it. It's all 2D. So right away, there's no W. I mean, mathematically, you may have it in some of the equations, but when we sketch something, it's always going to be 2D. So we're going to have this knife-edged flat plate. We have the fluid coming at it. We're interested in calculating at a particular point. There's the point right there. I would like you to be able to tell me what U is. What is that? That's the velocity at that point in the x direction, as well as what, and I'm not showing it to be even as large, V is. Now, the focus is 99.9% of the time on U. U at the location X and Y, not really V. Okay, so when you come in, we're going to introduce a coordinate system. Let's put the origin of the coordinate system at the tip. And we're going to run down this way. What are we going to run? What direction? X. And then what are you going to run out this way? Y. That's nice. That's really nice that we're going to put X and Y in that way. But it's going to be a little bit problematic or challenging for you to remember these things if you remember from fluid mechanics, because you'll say, come down to this location X right here. Just pick that. That's the distance from the leading edge. That's X. Okay. I want you to sketch the velocity profile. And so what you'd do is you'd say, well, it's going to come out like this. And way out here, it's all just U infinity. It's just U infinity, U infinity, U infinity. The presence of that knife-edge flat plate hasn't been felt deep into the fluid. So it's all just uniform velocity, just like it was uniform velocity when it was approaching the flat plate. But as you get close to the surface of the plate, what do we know about the boundary condition? It's a no-slip boundary condition. And so the velocity, u, at y equals to 0 has to be 0. What do you mean y is equal to 0? It's at the plate. So we have to come in and do that. And so what we're really interested in is how does u vary as a function of y? First time student sees that, it really is confusing. It's like, I want u as a function of x. No, no, no. We put x as the distance horizontal from the leading edge. Y is perpendicular from the surface into the fluid. That's why u is a function of y. That's what we're really interested in. All right. And then also, you know that way out here it's just flat. So you say, well, where is it that the action's happening? Where is it that it transitions from no slip to almost u infinity? Well, there's the question of what's almost? Well, 99% of. So if you say, I want you to find u, or I want you to find the y is equal to, let me write it this way, delta is equal to y. So evaluate u at delta, which is a boundary layer thickness, delta, which is basically how far out I have to go in the direction y, such that I'm not 100% to u infinity, because I'm starting at 0, but I'm getting close. And now how close is close? Well, I'm very happy to report that vast majority, I've never seen any fluid mechanics textbook, although I haven't done an exhaustive search of this, that says anything but 99%. When I first looked at this, I thought, well, probably some analyst is going to say 98%. Or some theoretician would say 95%. And then it would be very confusing, because I'd go to this book, and then the definition of the boundary layer thickness is 95% of u infinity, or 98%. No, I'm very happy to report 99%. Don't ask me why. Probably way back to some beginnings of the study of fluid mechanics, somebody picked it, and that's the way it stayed. If you come over here at this x, closer to the leading edge, well, this is always a challenge. It's still u infinity far away, and yet it's u infinity a lot closer before it does the transition. So this one's, again, a little tricky, but I will say that the velocity gradient is larger near the leading edge, meaning the change in u with respect to y evaluated at the surface, y is equal to 0. That there is larger. It's steeper. Now I know that this term throws students off, but it's steeper than this one. And then if you went further down, it would be less steep. Professor, I don't understand. Well, you have to rotate the coordinate systems if you want to do that. Put y down here, and then put your velocity profile like this, or like this, or like that. And now I think the terminology about steepness is more apparent. That would be at a smaller x, closer to the leading edge, further down, and then further down. It becomes less steep. But when you show it in this way, it looks like this is steeper, right? But anyway, the du dy at that location is not as large as du dy at the surface closer to the leading edge. Hey, wasn't fluid mechanics a challenging class? It sure was. It sure was. Because now you got to build on all that. So you got to get that straight. Okay. Let's continue on. Oh, clicker question. Multiple choice. For flow over a knife edge flat plate, what we've been talking about, which statement is correct about the location x? Does x range from 0 to L, 0 to infinity, negative infinity to L, or negative infinity to positive infinity? All right, remember that I tried to make a big deal that we introduce a coordinate system. X goes here and Y goes there. Are we really interested in anything other than X starts at 0? No. None of this negative infinity junk. That doesn't make no sense. Now, it starts at 0, and we're going to go down. Now, eventually, you could have a finite length plate, couldn't you? The plate could end, and we would call that the distance of the plate. So, you know, it's this one or this one. Let's take a look at what people said. We'll take both of those. But really, we're interested, X is really only going to go of interest because after the plate ends, this is no more discussion zone. We're just not interested anymore. It really is, X goes from 0 to L. All right. Oh, hey, we got another question. So same question, except what about this location Y? Y. Does Y go 0 to L, 0 to infinity to L, negative infinity to positive infinity? And we'll show the results. And it does go all to infinity. There's no length in the Y direction. We don't stop at L at all. No way. We just go off to infinity. So there you go. And the plate, again, we're just studying what happens on the top edge of that plate. The plate has to have some thickness, and nobody's doing this. If they did, it would be ultra thin plate, and then it would just be the symmetry. So nobody talks about what happens below the plate. It's always what happens above the plate. So we're very much interested in this velocity boundary layer. So again, sketch the beginning of the plate. We come down here. We can sketch out the region that the velocity profile, let's say at this location, you come out that far, and at this location, the velocity is 99% of U infinity. And so that gave us that criteria for the thickness of the boundary layer. So U at any X, you're gonna see that this changes as I go further down in X, right this way. What happens? The boundary layer thickness increases. Okay. Where Y is equal to the boundary layer thickness is equal to 99% of U infinity. Okay. In addition to the thickness of the boundary layer, we're very much interested in the viscous shear stress. And so we have an equation from fluid mechanics, the law of viscosity, that tau is equal to mu du dy. Where did that come from? The law of viscosity. Maybe you have a different name for it in your other fluid mechanics textbook, maybe not. Most of it's just called the law of viscosity. Here it is. So the shear stress at the surface, S, I evaluate that du dy at the surface, S. And so I'm interested in that slope right there at the surface. And if you go ahead, and we already talked about that, but it's steeper here. It has to have a more, it's steeper like that. Well, red color. And then it less steep as you go down. So the shear stress early on, close to the beginning of the plate at the leading edge, is larger. Okay, so that's the surface shear stress. Hey, what are the SI units for this surface shear stress? Tau sub S. And then you can do this one and this one, because that's equal to something multiplying something. So let's just get it for tau first. Newtons per meter squared. Thumbs up? Very good. All right, let's come over here now. Du dy. That's a ratio of a change in U, which is U is a meter per second, over a change in Y, which is a meter. SI units look okay? So that would boil down to per second. So what has to be the units of mu, Newton? Let me boil this down. This is 1 over second, right? Newton second per meter squared, true or false? Okay. What's the name of this mu? Viscosity. Absolute viscosity. And those are the units for absolute viscosity. All right. The boundary layer thickness is a function of x, y, or both, or neither, or something. Delta. So professor, draw that sketch again. Here's our sketch. And so the x is running down this way and the y is running out that way. And we really have this, a lot of times dashed, and they're drawing this delta, right? And so would it be more appropriate to say delta is a function of y? Or would it be appropriate to label this and say delta is a function of x? Or would it be appropriate to label it and say delta is a function of x and y? Well, what was the definition again? Well, the definition is we want to know for a given x where y is equal to the boundary layer thickness, it's 99% of u infinity. How far out do I need to go at a particular x such that the velocity is 99% of the free stream? With that discussion, re-answer the question. The boundary layer thickness, is it a function of x, y, both x, y, or neither? And we'll show the results. Well, this box is always in my way. I'm going to grade it like that. Put it down here. It is at a particular x, how thick is the boundary layer? At a particular x, how thick is the boundary layer? At a particular location from the leading edge, how thick is the boundary layer? This is the best expression. The thickness varies as a function of distance from the leading edge. The boundary layer thickness. Okay, let's see if I helped anybody. There were 9 correct, or 30% of the class. Okay, well, just a few helped a little bit. Okay, now let's press forward. This question's, maybe I'll answer it. In the velocity boundary layer, we are primarily interested in solving for, well, here's our flat plate like this. This is the x going that way. This is the y going that way. What I would like to know is, at this location, what is my viscous shear stress? Tau at the wall or at the surface. To do that, I need to know the fluid property, and I need to know the rate of change of u with respect to y evaluated at that surface. Y is equal to 0. All right. Now that does change as I change location x. I go further down, further down, further down, or closer to the leading edge. It does change. The wall shear stress does change. If I actually go back in fluid books, they'll show tau sub s, and they'll plot it, and they'll be like, well, there's a little problem here at the tip, because what actually happens is the boundary layer thickness goes to 0. And there's infinite, slope right there. And so this goes to infinity, but don't worry about that. It does some shape like that, comes down, right, with a singularity at the tip. So we're interested in u as a function of y, and then the gradient of it evaluated at the surface. Okay, so of all of these, I would say u is a function of y at some specified location x from the leading edge. That's the best answer. Here's maybe a summary. So again, there's some singularities right here at the tip, but don't worry too much about it. U infinity is approaching, it's uniform, it's well aligned with the flat plate. We're interested in the velocity profile. Far away, it's all U infinity. Some boundary layer thicknesses where the velocity U component is a function of Y, and it's up to the point where it's 99% of U infinity. All right. What are we really interested in? What's happening at the wall? Law of viscosity. So we need that derivative. Then what do? We have this as in newtons per meter squared, and you want to normalize it. That's the trend. You generalize by introducing these dimensionless groups of terms, and then you can extrapolate the results to many other cases. So they introduce what's C sub F? Friction coefficient, or skin friction coefficient. And how is it defined as? It's defined as tau sub S divided by, hey, what is this term? Very often you see that term, 1/2 rho U infinity squared in fluid mechanics. What's the name of 1/2 rho U infinity squared? What would they call that group of terms? Dynamic pressure or velocity pressure, right? All right, well, okay, the wall shear stress is one of those, A, B, C, D, or E. And we show the results, and okay, maybe I do this too. I'll move that over here. It's the derivative of some slope at y equal to 0. So at x equal to 0, that would be at the leading edge. So this one, the wrong location, so those are out. And then it's how the component of the velocity in the x direction, u, how does that change as I'm moving further away from the plate into the y direction, So it's not a v. What is v? V is the y component. No, so that's garbage there. So this is a du, there's a duy. And now it's how does it change with respect to y? And this is how it changes with respect to x. No, here it is. How does u change with respect to y at the surface, y equal to 0? That's the best answer, E. Okay, so we have some equations for the wall shear stress. What was our symbol for that? Was that tau? Tau subscript S? How did you calculate it? Mu, a property, times du dy at y equal to 0. Okay. Then we had our skin friction coefficient. What was our symbol? C sub F. What was it defined as? Tau sub S divided by our dynamic or velocity pressure. Most people would call it dynamic pressure. 1/2 rho. Is it u squared, or is there a subscript on that u? Infinity. U infinity. Very good. U infinity squared. Hey, what is rho? Mass density of the fluid or the mass density of the plate? Mass density of the fluid. Yeah, right. Now, if you have an average value, what do? Well, you would say tau, and I still want it at the surface, but I'll put a bar on that. What does that mean? Average. So you have this as a local, as a function of x. So if I take tau sub s and I sum it over all the x's, the integral from 0 to L or 0 to a new x, this could be confusing. Let me put L equal to 1 over L times the integral 0 to L of tau sub s dx. What are we doing there? You're averaging over the plate from the leading edge at x equal to 0 to the trailing edge at x equal to L. Okay. Somebody says, I want to get really confusing. I want you to average, they'll put tau sub s. I don't want you to average from 0 to L. I just want you to average from 0 to x. You can do it. It's just 1 over the length x integral from 0 to x of tau sub s dx. The notation in the subscripts can get a little challenging. Somebody says, well, I really want to emphasize that this is a local. So I'm going to put tau sub s comma x, subscript x. So that's really emphasizing that that's the local local wall shear stress. And then over here, maybe put the x inside, and maybe that makes more sense. All right, notation can be challenging. Now, what about the average skin friction coefficient? Well, C sub f average. Do you want to average from 0 to L? Sure, do that way. C sub f dx from 0 to L. That'll work. Or if you want to average only from 0 to x, you can do that. I mean, in general, if somebody gave you a function, let me insert a new page. Insert new page. Somebody said, here's my function of x, and I want you to get f average of x from the x equal to a to x equal to b. So let me try and graph that. Here's f. It's a function of x, and maybe my function does this. And they say, now I want you to go out to a, and I want you to go out to b, and I want you not only to evaluate f at a, that would be this magnitude right there, or f at b, that magnitude right there, but I want you to give me the average function over the range a to b. Well, wouldn't that be 1 over b minus a? Isn't that length? The integral from x equal to a to x equal to b of f of x dx. Look good? There's no end to this. I mean, we can have all kinds of mathematical fun in fluid mechanics. Let's continue on. All right. Now we need to talk about temperature and temperature field, just like we talked about the velocity field. We need to talk about the thermal boundary layer. Well, I like to, you don't have to, I like to think of the surface is hot. And what's the fluid? Cold. So I know the direction of heat transfer. It's from the hot surface into the colder fluid. So we have our plate like this. And what's the temperature anywhere out here? It's all just T infinity. It's a uniform temperature. It's cold. It's going to strike and flow over this hot plate. So I pick a location x. This is, again, our coordinate system starts at x equal to 0 and runs all the way down x. Pick a location right here. And I say, what's the temperature in this location? Well, this is a little tricky again, but you're going to plot just like you plotted u infinity. We're going to plot T infinity like that. So everywhere way out here, it's all T infinity. What's T infinity be represented by? The length of this line right here. And it's the same length for large y's far away into the fluid. But then as you get closer to the plate, what does this temperature profile do? Does it stay flat? Answer A. Does it dip in? Answer B. Or does it kick out? Answer C, multiple choice. You tell me what's a sketch of the temperature profile look like, especially as it gets close to the surface of that hot plate. And again, you have to pick one. If the plate was cold, it would look like B. If the plate's hot, it looks like C. So it's this. That's what it looks like, isn't it? Because doesn't this represent the magnitude of the temperature in a longer line? Higher temperature? Yeah. So let's grade it. Okay. So there you go. So this is the temperature profile. Well, you can introduce the concept of delta T. Held it. I was introduced to delta already, but delta T, what do you think delta T is? Thermal boundary layer thickness. What do you think the criteria is for the thermal boundary layer thickness? Within 99%. But because the boundary condition doesn't start at 0, what we want to do is we want to introduce something else. It's theta, or the book will sometimes use T asterisk. It's a dimensionless temperature difference ratio. Okay? If we want it to go, if we want theta at the surface to be 0, how about put T minus Ts in the numerator? And if T at the surface, if theta at the surface would be, hey, I would have Ts minus Ts, that would be 0. No matter what I divide by, it would be theta would be 0 at the surface. And then we would want theta to be 1 far away, so you would divide by T infinity minus Ts. So check it out. Theta at y equal to 0 is 0. Theta at y goes off to infinity is equal to 1. Now I have a nice criteria. Yes, sir. The plot, really you want the theta to be 0 to 1. That gives us a definition for this boundary layer thickness easily, so that theta at y equal to the thermal boundary layer thickness is 0.99, 99%. All right. If you wanted to, you could go in and plot theta. Maybe the plot gets a little confusing here, but it would go from 0 out to 1. And I didn't draw it very good because it's going to be messed up. But I think you can plot theta. All right. What are you especially interested in? Not only solving for temperature at any distance down from the leading edge and any distance y up into the fluid, what are you really interested in? We're interested in predicting this, Q double prime. Okay. How am I going to calculate Q double prime? Well, at the fluid, isn't there still no slip? If there's no slip at the surface, at that millimeter, micron, whatever layer, very thin layer of fluid is stagnant right there, you have to be conduction pushed into the fluid. So they'll say at the surface, it's Fourier's law. They'll have minus K of the fluid, not K of the solid. So many students will think that, I got to get the K of the solid surface, that the plate, what is the plate made of? Stainless steel, aluminum, copper, whatever. No. They'll put an additional subscript F sometimes, the K of the fluid, and then they'll have the rate of change of temperature with respect to Y at Y equal to 0. Isn't that our Q double prime? And the way it is if it's hot like this, it's getting colder as I move into the fluid, hence the negative sign's needed, and the math does work. All right? So what is, let me go to the next slide. Let me build this, continue this on the next slide, because what I have here is a cleaner plot. What do we have here? I'm talking about that derivative right there. And so we have that Q double prime at the surface is minus K of the fluid, the rate of change of temperature with respect to Y at Y equal to 0. Sometimes I'm a little sloppy. Sometimes I'll put dt dy. I know the difference between an ordinary derivative and a partial derivative, yes, because t is a function both of x and y, I should put the partial derivative. But every now and then I'm just thinking of, at this location x, I know t as a function of y, hence I'll put it as a ordinary derivative. Anyway, let's continue on. Now, if I can get that, that gives me my Q double prime. How am I going to use my Q double prime? I'm going to go back to the Newton's law of cooling and have H is equal to Q double prime at the surface divided by the temperature of the surface minus the temperature far away. My goal is to get H. If I knew the temperature profile, I get the slope of the temperature profile. this is how I get H. It's pretty abstract, isn't it? But a lot of fluid mechanics is pretty abstract. So we can substitute. We have H is equal to minus K sub F, the dt dy at y equal to 0 or at the surface, divided by Ts minus T infinity. You go back and you say to yourself, what exactly was our definition of theta? Right here it is. Isn't that our good definition of theta? Okay, do me a favor. Can you calculate the, I'm going to just leave it, I know it's partial, but leave it ordinary derivative, d theta dy. What is that equal to? Just, how about if I pause, walk around? Here's my equation for theta. Show me what is d theta dy. And then I'm going to compare that with this over here and make a simpler equation for H. I get tired of standing. I want to exercise my legs. So you have the constant T infinity minus Ts. That just is staying there in the denominator. And then you'll just pick up dt dy. Right? Right. And so if you look at it, you have this. If you now evaluate that at y equal to 0, and you evaluate y equal to 0, what is all of this with the minus sign? Isn't that k sub f times d theta dy at the surface, or y equal to 0? Doesn't it? And so the minus sign takes care of itself and everything works out, although now it's so abstract I'm completely lost. So what is theta again? The temperature difference dimensionless by dividing by a ratio. But anyway, there you go. So if somebody says, I really want H, how do I get it? If you really knew the velocity profile and the temperature profile at the surface, really it's the temperature profile, then you could take the derivative of it and get H analytically. All right. What happens once I have a local H? Guess what I can do? Average. Does this equation look familiar for averaging? 1 over L's integral from 0 to L of the local H? Sure. Sure. Okay. Hey, that's the equation we just had, didn't it? Isn't that what we just established? Okay. Oh, try to summarize. There's a lot of things. We're talking about wall shear stress, the friction coefficient, and then we could have the local and the local at the trailing edge, L. We could have the average up to some arbitrary from 0 to X, or the average from 0 to L. Likewise, local skin friction coefficient, the local skin friction coefficient at L, the average from 0 to X, or the average 0 to L. Now you add the local convection coefficient, the convection coefficient at the trailing edge at X equal to L, the average from 0 to X, or the average 0 to L. Nusselt number. What's the Nusselt number? For our case, because we're doing a flow over a flat plate, if you wanted to emphasize the length scale, you'd put a subscript X. Nusselt number, local Nusselt number as a function of X would be the convection coefficient at that location X times X divided by K. So that's what this is right here. And then you could evaluate the Nusselt number at the trailing edge at X equal to L, get the average from 0 to X, or the average from 0 to L. Okay, Reynolds number. We could talk about the Reynolds number at X. We could talk about the Reynolds number at X equal to L. What's NA mean? There really is no discussion of an average Reynolds number. I mean, it starts at 0, the leading edge, and we know how the equation is. What's the equation for the Reynolds number? Sometimes it's a U infinity times X divided by nu, or you could put mu over rho instead of dividing by the nu. Right? Isn't nu equal to mu divided by rho? Yeah, very good. All right, so at least some of these don't make any sense. But the rest of them, sometimes that's the way the problem is worded. Air at 107 degrees C and this many meters per second flows over a knife-edged flat plate, and the plate is at a temperature of 47 C. So what's hot? The air is hot. And what's cold? The plate. But the math works itself out. Okay. The temperature distribution in the boundary layer is given. I don't know how they did it, but there it is. They give you a nice analytic expression. T minus Ts divided by T infinity minus Ts is 1 minus exponential minus Prandtl number. Hey, what was that Prandtl number? Nu over alpha. That's not a V, that's a nu. Okay. And then you have U infinity Y divided by nu. Okay. Where they give you the value of K, Prandtl number, and that kinematic viscosity nu. Calculate the surface heat flux. How would you calculate the surface heat flux, Q double prime at the surface? Minus K of the fluid. This is the K of the fluid right there. Times the rate of change. I'm going to put just ordinary. T dy at y equal to 0. So I have to take this function. It's a function of y right there. And I have to differentiate it. T is a function. Can you do that derivative? Well, I would rewrite this equation as something like T is equal to T sub s plus T infinity minus T sub s times 1 minus the exponential of minus Prandtl times U infinity Y divided by nu, close. Can somebody give me the T dy? And then we're going to evaluate at y equal to 0. Wouldn't that be equal to T infinity minus Ts times? Now we're going to put the minus, then we're going to have this minus Prandtl U infinity divided by nu exp of minus Prandtl U infinity y divided by nu. Did I do that okay? Thumbs up if you agree. Very good, thank you. Now we evaluate it at y equal to 0. So what happens when y goes to 0 right here? It's exponential of 0. What's the exponential of 0? E to the 0. 1. Very good. So this whole term is just 1. And you can continue the math. So the derivative of the temperature at the surface is equal to T infinity minus Ts times Prandtl U infinity divided by nu. Okay. We multiply that by to get the surface heat flux minus K sub F, and then all of this. Now, will I get a negative Q double prime? What does that mean if it's negative? Well, it's flowing from the hot fluid into the cold plate instead of the hot plate into the cold fluid. The sign even works. Okay. All right. Just bring that down. And when we calculate the values there, it comes out to be negative 3,660 watts per meter squared. Will the units work? Chase your units. Work slowly. Make sure your units work, and they do work. What's the next one? What is the convection coefficient? H. So H, what's my equation for H? Yeah. Q double prime S divided by, then we, all right. So it'll be this negative 3660 watts per meter squared. And then the surface temperature was cold 47 minus the warmer 107. Actually, that gets rid of the negative sign. And so your convection coefficient comes in at 61 watts per meter squared degree C. That work? So testing again your calculus skills. Oh, there's the solution worked out. Why didn't you just show us that in the first place, Professor? Okay. An ideal gas has the dynamic viscosity. What is the dynamic viscosity? Mu, not nu, mu. All right. The thermal conductivity, K. The specific heat, C, or C sub P, both specific heats, are approximately independent of pressure. Where did this come from? A lot of observation, and it's supported by theoretical analysis or models for what an ideal gas is. So mu is a function of temperature only. You neglect the effect of pressure on an ideal gas's absolute or dynamic viscosity. Likewise, thermal conductivity is a function of temperature only. C sub P is a function of temperature only. Okay, so here's a bunch of questions. We want to explore this. First of all, what is the viscosity of air at 350 Kelvin at 1 atm? How would you calculate that? You need it for a problem. Somebody says, I want you to get and this would be the dynamic viscosity of air, mu, at 350 Kelvin, 1 atm. How would you do it? You have appendix in the back of the book for properties. So you go to the back of the book and there's table A4, thermal physical properties of gases at 1 atm. It starts off with air. There's a whole bunch of them, helium. The table's long. Table A4 is long. But we come down here, what did we say, 350 Kelvin? Isn't that the one? And look, if you wanted to know the density, specific heat, viscosity, mu, this is also viscosity, but it's a kinematic viscosity, nu, or thermal conductivity, thermal diffusivity, or Prandtl number. There you go. How many people know how to handle this 10 to the 7, 10 to the 6, 10 to the 3? You got to be careful on that, right? Don't forget the headers. Now, what pressure are these all at? Atmospheric pressure. Because you know that density is like, hold it, how can you put in a table the density of an ideal gas like air? Because if I change the pressure, isn't the density going to change a lot? Yeah, look, what's the equation for the equation is that P is equal to rho RT. So if I increase the pressure, and leave the temperature alone, what does rho do? Goes up. So if I doubled the pressure, let's say I wanted at 2 atm, 2 atmospheres, what would I do to this density? Double it. But what did they say about the thermal conductivity, the mu, and the specific heat? Those are not functions of pressure. They are negligible functions of pressure. Only extreme pressures would they really kick in. Okay, so density is a function of pressure. Okay, not a function of pressure for this one, or mu. What about nu? Well, look at nu is mu over rho. So if mu is not a function of pressure, but rho is, and I double the pressure, rho doubles, what happens to nu? Does it double? No, it goes by half, doesn't it? Yeah. K is not a function of pressure. What about alpha? Well, alpha is K divided by rho C. Rho is only a function of pressure in that equation, only one. K and C are not. Hence, if you double the pressure, the alpha goes down by a factor of a half, or it's multiplied by a half. Okay, what about the Prandtl number? Prandtl is nu over alpha. we just looked at nu, that's equal to mu over rho, and then we have alpha is K over rho C. Rho's cancel? Guess what the Prandtl number is? Essentially independent of pressure. Okay, so good. Let's back up now. And you could say, just give me the dynamic viscosity of air at 350 Kelvin. What I'm going to do is I'm going to open up now a numeric response. And what are we asked to solve for? The dynamic viscosity. Okay, I'm going to now, you have to remember this, I'm going to move away from it. What temperature? 350 Kelvin. What pressure? 1 atm. And now, I'm going to leave this table up as you answer that question. So, what units, you can't type in for a numeric response to units. So what units are you going to assume for this answer? Newton second per meter squared. So just give me the numeric response. What's in the header? All right, let's take a look at the results. Oh, look at that. E to the plus 9, though. Why do we have plus 9?
Yeah, so on the phone, it automatically corrected it.
Yours is not up there?
No. Oh, no, they're all up there. The iClicker automatically corrects it to the plus 9.
Oh, it does it? But it needs to be a negative 9.
There is a negative 5.
So this one is close. This is actually the right one, right? So that one's correct. We'll take this one as correct. So wait, I want to, oh, it's still grading them. Allowing them. I'll have to stop before we grade. All right, so this is correct. That's correct. No, with the pluses. Oh, we'll take that one. They had problem. In this one, I'm sorry, you got to look at the header and know how to deal with the header.
I think it recorrected all.
Well, there's a lot of fun to be had. Now, somebody says, what's the dynamic viscosity of air at 350 Kelvin, 5 atm? Oh, you changed it. Without knowing that the dynamic viscosity, kinematic, or thermal conductivity, or the specific heat are not functions of pressure, they're essentially independent of pressure for ideal gases, you'd spend a lot of time looking. You'd get very frustrated. But guess all you have to do is you just have to go and say the same value. It's the same for that property. Then the density of air. Well, 350, 1 atm. You go to the table. It's the right 1 atm. And you're there 0.9950. But then the next question, say the density of air, same temperature, but 5 atm. Right. So basically I would do this. Say, we know that the pressure is proportional to the density. Okay. So that if I have the pressure, well, let me do it this way. If I have the density at 1 atm and I divide it by the pressure at 1 atm, that's simply just density. It's 1 over RT. It's a constant, which is the same as the density at 5 atm divided by the pressure at 5 atm. So the density at 5 atm is equal to the density at 1 atm out of the table. Then you multiply by the pressure at 5 atm divided by the pressure at 1 atm. This seems a little funny because what's that ratio? 5. It's like 5 over 1. It's just 5. Maybe that helps you, but you would just multiply the density times 5, and then boom, you'd have that answered. What about the kinematic viscosity? Well, you have to know the kinematic viscosity nu is mu divided by rho. Mu is not a function, rho is. And so what you do is you say, okay, then the nu at 5 times the rho at 5 is a constant, which is the nu at 1 atm times the rho at 1 atm. So the nu at 5 atm is the nu at 1 atm times rho of 1 divided by rho of 5, or you divide by 5. So there you go. For this one, for 5 ATM. Okay, thermal diffusivity, same thing. Go slow, you can work it out. I'll leave that in the interest of time. Let's press forward. Okay, another problem here. The local convection coefficient is given by this equation, where x is in units of meter and h is in units of watts per meter squared degree C. Calculate the local at x equal to 0. There's the answer. I guess it's not that challenging. Can you see why the answer is 25? Yeah? Give me a thumbs up if you follow that. Good. How about the local at x equal to 3? So here's like the leading edge, the trailing edge is 3 meters. Okay. Can you see where it's 7.6? You would just stick it into the equation, 3 into the equation, and then you go. Actually, if you plot it, and that's usually a pretty good thing to do. Oh, it starts at 25 and it's going to go to 7.6. Looking at this equation, it's just a quadratic downward, shaped. It's not, somebody says, well, how come you don't know if it starts at 25, goes to 55, and then back down to 7.6? No, look, it's a quadratic. Just look at it, plot it. Pick a couple more points and just evaluate it. It's kind of a boring little plot, isn't it? There you go. All right, now, what's the average between 0 and 3? What's the average between 0 and 1? What's the average between 2 and 3? So all of those are just worked out. Average between 0 and 3 was, 1 over 3 minus 0, that's the length. The integral from 0 to 3 of that equation plugged in dx. 0 to 1, there it is. And then from 3 to 2. All of this just a good application of calculus and integration. Oh yeah, I copied that wrong. That should be from 2 to 3. Perfect. Thank you. Look good? You can do that? Thank you. Well, how do we get the detailed solution for these equations for the velocity and as well as the temperature? Well, you go back to your fundamental equations. These are the boundary layer equations. This is the continuity equation. This is the momentum equation. This is the energy equation. All right? These two you're familiar with from fluid mechanics. This is the only new one. Okay, the continuity equation. Can you just look at it and see what are your assumptions? It's two-dimensional. It's steady state. And there's no change in density anywhere. It's constant property. Density. So that's going to make it simple for us. We don't want density as a function of location because the temperature's a function of location and it's less dense when it's hot. That's natural convection, another chapter, another day. So what about this equation? This is just one of the two momentum equations. Don't you have the momentum in the x and momentum in the y? Can you see which one this one is? Here's the big hint. The change in the pressure with respect to x. It's the x direction momentum equation, not the y. All right? Basically, the fluid, once it hits a little bit above that, you're looking at the flow in the boundary layer above the surface of the plate, it's slowing down in the x as the momentum is felt, the viscous effects, further up above the plate. All right. Isn't this how the diffusion of momentum percolates or moves and is felt in different layers further and further into the fluid above the surface? Yes. And what is this? The advection of momentum. All right. Well, if you can understand this equation, you just look at it. What is this? Advection of energy or internal energy. I know that they've taken the specific heat out. And what's this look like? That looks just like this one. This was the law of viscosity, diffusion of momentum. This is Fourier's law, diffusion of heat or internal energy. Okay, this term is kind of a crazy term. Anybody want to guess what that term looks like? Because you did have the energy equation in your fluid mechanics text. But what is that term? Only you wouldn't probably recall. It's a viscous dissipation. It's the kinetic energy goes to internal energy. Or mechanical energy goes to thermal energy. Because this energy equation is not the complete energy equation in the sense that you're not tracking the changes in kinetic and potential energy. You're just changing the enthalpy or the internal energy, so that this shows up as a source term in our energy equation. Why? Friction and the mechanical energy is being dissipated through friction. All right. A lot of times that term, thankfully, is negligible. Things flow from hot to cold, and that's the predominant way that energy is changed, not that it's a viscous dissipation. All right. In these equations, you can cast them in dimensionless form, and you can get some dimensionless parameters. One is the Reynolds number. Okay. Let's put it as a function of location x. What would it be? Rho u infinity x divided by mu, or u infinity x divided by nu. What's it a ratio of? Inertial to viscous forces or stresses. All right. What about the friction coefficient? Well, let's do the local friction coefficient. What was it? Tau Sx divided by 1/2 rho u infinity squared. Ratio of the surface shear stress to the dynamic pressure of the flowing fluid. Okay, Nusselt number. Nusselt number is a function of x. It would be our h at that location x times x divided by k of the fluid, thermal conductivity. This is a little more abstract, isn't it? It's related to the gradient of the dimensionless temperature profile in the fluid. It's a little more abstract than the first two. You have better physical interpretations for the Reynolds number and the friction coefficient. All right. Well, you take each of those equations, and I don't do it, I didn't do it, it's in the book or it's summarized in the book. And you apply your calculus rules of calculus, to change variables. So what we have is we want to introduce a dimensionless pressure, a dimensionless velocity in the x, a dimensionless velocity in the y, dimensionless length scale in the x, and a dimensionless length scale in the y. All those hopefully make sense. I can't get that out of the way. Fine, move it. Okay. So here is just that x momentum equation. So what I did to try and show it is if I take this equation and I divide by u infinity here, and I divide by u infinity here, and then I multiply by u infinity squared on the outside, I really didn't do anything, right? I multiplied by and divided by the same term. So divide by u infinity right here, divide by u infinity right there. That means I would have to multiply by u infinity. Okay. Likewise, if I have an L over L here, I have one L there, and then inside I'm going to put x over L. So the derivative with respect to x over L. There's a couple ways to do this. Now I see, oh, I now have x star. So it's differentiating with respect to x asterisk or x star. And then in the numerator, the derivative with respect to u asterisk or u star. And then it's multiplied by u star. It's changing the variables. Do you see how that one was done? That's one way of describing it. There's other ways of describing it. Likewise, you would have the same u infinity squared, and then you do it with v asterisk, u asterisk, y asterisk. Okay, how about for the pressure? Very similar. I want to divide by rho u infinity squared, so I have to multiply by rho u infinity squared. And then I want to put over an L here, and I already had a rho on the outside. This rho already on the outside. And then once I have them all, how do I describe this, set up, then I take and divide or multiply the whole equation by 1 over u infinity squared, or L, maybe I should have done that, multiplied by L over u infinity squared. That way the L's cancel, the u infinity cancels. It does it on this term right here, but then doesn't do it completely on that term, because what you're left with is this group of terms after you do some algebra. And then you stare at that term and you say, oh, it's the upside down Reynolds number. It's the reciprocal, the Reynolds number. So the Reynolds number, this function of L, is rho u infinity L divided by mu. So I cast our momentum equation into dimensionless form. You have to do that for the continuity, easy. The momentum, pretty hard. I just showed it. And then you have to do it for the energy equation. Once you do that for those three equations, you'll get the momentum, or the velocity as they call it. This is the x velocity or x momentum. That's the one I tried to summarize. What shows up in it? Reynolds number. The rest of it's dimensionless. You then have to cast over the boundary conditions. So here's my differential equation. I need boundary conditions before I could theoretically look for a solution. This would be what's happening at the wall. How do you interpret this statement right here? At all x, at y equal to 0, what is this? No slip boundary condition. And then what about this one? It's our free stream boundary condition. I'm not certain why they have cap V here. It basically is 1. This u asterisk goes off to 1. This is u infinity. Okay. And then what is your similarity variable or parameter, dimensionless parameter? It's a Reynolds number. Now, you do the energy equation or thermal equation. They already dropped the viscous dissipation term. So you just have the advection and you have the diffusion of energy. And you pick up, after a little bit of work, 1 over Reynolds Prandtl. You then look at casting this one, the wall, you get the T asterisk, or theta as I like to call it, it's equal to 0. Look at, that's very similar, isn't it? U and T asterisk, very similar. And then here, instead of U asterisk being equal to 1, you get that T asterisk is equal to 1 far away in the fluid. Very similar boundary conditions. So it's like the boundary conditions are the same, the structure of the equations are the same if this term is negligible, and then the Reynolds is the driving parameter in the velocity, and the Reynolds times the Prandtl is the driving parameter in the thermal. What do you want to do? You want to solve this one to get C sub F. You want to solve this one to get the Nusselt number. So the definition of the C sub F, if you're able to solve for U asterisk from the velocity profile, is to get the derivative at the surface, and then you have 1 over the Reynolds. This is, I know it's a little abstract, but there you go. And if you look at it, this derivative is simply a function of the location from the leading edge and the only parameter that drives it, which is the Reynolds number. Okay. Again, this term right here is going to be negligible. The Nusselt number, I want the derivative of the dimensionless temperature, T asterisk, at the surface. I look at it, if it's a function of the Reynolds and the Prandtl and that location. All right. If the Prandtl, I know this is getting to be pretty abstract, that's why I'm trying to summarize it pretty fast. If the Prandtl is about 1, these functions are the same, and that's the Reynolds analogy. So the Reynolds analogy says that this function here is the same as that function. Hence, the C sub f over 2 times the Reynolds number, they pull that up there, is expected to equal the Nusselt number. For a limited case, how the drag force is induced on a surface tells you how the convective heat transfer will be from that surface. That's the analogy between the momentum and the heat. Okay. Now, a lot of people, when Reynolds developed that, looked at it, they said, you know, this assumption about the Prandtl number being close to 1, yeah. But you know what? If you modify the experimental data by having the Prandtl to the 1/3, it improves the correlation just a little bit, so they call it the modified Reynolds analogy, sometimes the Chilton-Colburn analogy, but it's modified. This is the one most people will use. Atmospheric air at 15 C and for 15 meters per second at 15 C is a free stream condition, flows over a given 0.25 meters squared surface and induces a drag force. So somehow the drag force will allow me to calculate the shear stress on the surface, which will allow me to get the skin friction coefficient. From the skin friction coefficient, I'll use the Reynolds analogy to calculate the Nusselt number. From the Nusselt number, I'll calculate H, and then from H, I'll be able to get what sort of power is required to keep the surface hot. What? Only from some measurement of the drag force? Yeah, only from measurement of drag force. So, but this is, the key here is the problem forces you to use that Reynolds analogy. Okay, so let's take a look. Yeah. So the area in the force gives you the shear stress. That's how many newtons per meter squared. Gives you the shear skin friction coefficient. You need to get the density. You figure out the average fluid or the film temperature for your property evaluation. You would just say, well, look, at the surface is 15, and the fluid is at 15 and the surface is at 140. Add them together, divide by 2. It's around 77 degrees C, 350 Kelvin. You need, the properties are temperature dependent, so you need a film temperature for that. You get your density, viscosity, thermal conductivity, diffusivity, Prandtl number, all out of that table. What was it, A4? For air, 1 atm. Okay, so that's how you need that density. You calculate skin friction coefficient. The Reynolds number you calculate. Now you use the modified Reynolds analogy to get the Nusselt number. Unravel the Nusselt number to get an H. Use the H in the convection equation to get the Q, and that's the electric power. It's got a balance because that's what's being cooled, the rate of cooling of the surface. 660 some watts. Doable? All right. Another problem. So we have forced air. It's at the given temperature of 25 C and 7 meters per second is used to cool electronic elements on a circuit board. One such chip is a small 4 millimeter by 4 millimeters square. It's located 120 millimeters from the leading edge. So here's the beginning. You go down at a length of 120. You get a little 4x4. So this is really not showing the scale. What are they doing there? It's a lot further away from the leading edge. And then you have this little chip, which is 4 millimeter by 4 millimeter. And the chip is dissipating heat. Okay. From experiments, convection heat transfer is correlated by the expression of the form, and I covered it up. Let me move this out of the way. Here as it is. Local Nusselt number is 0.04. The local Reynolds number to an exponent of 0.85. and then the Prandtl to the 1/3. Again, that Prandtl to the 1/3 is often the structure of the modified Reynolds analogy. Okay. The chip dissipates 30 milliwatts. What's the temperature of the chip surface? And there's the value, but how do we calculate it? Well, we're given Q 30 milliwatts, and it has to be HA T surface minus T fluid away. So T surface will be the fluid temperature far away plus the rate that heat transfer is dissipating, 30 milliwatts, divided by HA. I need to calculate H. How do we get H? Well, H is equal to some Nusselt number times some thermal conductivity divided by some appropriate length. This is where we think, are we interested in a local H or an average H? Some H beginning and going from 0 to L, is that what we're looking for? Or the H at L of 120 millimeter? Well, because it's only plus and minus 2 millimeter around 120, we're looking for a local. So here it'll be HX, you can put an X on there, an X on there, and you divide by X, the length scale. So that was a big decision point, because this is a local Nusselt number equation. Thankfully, I don't have to average it. I just have to use it. Okay. So I need to use this equation to get Nusselt so I can get H. All right. So before I use that equation, what do I need to know? My Reynolds number. So my U infinity, my X divided by my nu. I need to get my properties for air. So because we have air right here, we have to do some estimates. Okay, we know that the air temperature is 25. Our table has them in Kelvin. That's around 300 Kelvin. How hot do you think the chip temperature is? This is one of those guess the final temperature, make the evaluate the properties using the film temperature, make the calculation, and then see if it was close. You may have to iterate. But let's say that we want to guess that it's about what? A little over 300? No, it looks like I ran with 300. So my U infinity, 7 meters per second. My distance X is 0.120 meter, and I divided by 15.89 times 10 to the minus 6 meters squared per second. The units work, we get a Reynolds number that's 52863. Then we put that in there. So we're going to get the Nusselt number, 0.0452863 raised to the exponent 0.85. The Prandtl number I used was 0.707 to the 0.3333 or 1/3 exponent. And then you get the Nusselt number is 368.59. Too many digits, but hey, you're just intermediate calculations. Keep them all. The local H is the 368.59 times the thermal conductivity, 0.0263 watts per meter Kelvin, divided by the distance 0.120 meter. So you get the local H is around 80.78 watts per meter squared Kelvin. Hence, we can calculate TS is the 25 fluid temperature plus my 0.030 watts, 30 milliwatts divided by 80.78 watts per meter squared Kelvin. And we have the area, which is 0.004 meters squared, and you get the final surface temperature around 48. Now, to improve the answer, get a better estimate of the film temperature, it would require you to interpolate to get the fluid properties. What pain? And it probably only changed that third digit. Probably not change the second digit. Okay. All right. We're about out of time. There's that solution. Maybe I should have just shown you the solution. And let me just try and emphasize what we've covered today. The name of the game when you're talking about convection is to find H. How do you find H? Find Nusselt, because the Nusselt is defined as H L, or let me put an X here, L over K. So I can unravel the Nusselt to find the H. And then how do I get the Nusselt? Well, the Nusselt is often a constant, Reynolds to a power, Prandtl to the 1/3. Look at the equation here. From the structure, some exponent on the Reynolds, some exponent on the Prandtl, and some constant. They get more complex, but the simplest forced convection ones are like this. When you get to natural convection, we have to go back and put a buoyancy term in our momentum equation, as well as how it affects velocity in our heat equation. But hopefully this chapter is a review of a lot of your fluids. Thank you very much.